Our last speaker in this session is Francesca Castaldo, and I'm very much looking forward to your talk. And we'll need to close this video and then see the...
Okay, let me share my screen and let me know if you can all see this.
Okay, there it is. Synchronization in the Connectome. Well, like that looks just like such a good fit to the previous talk. Very much looking forward to your talk, Francesca.
Yeah, more on the macro scale, but yeah, let's see. So, hello everyone. I'm Francesca, PhD student at the Wellcome Center for Human Neuroimaging at the UCL in London. And today I'll present the key results from a whole brain modeling exercise applied to MEG signals. So it's now well established how different oscillatory patterns promote different functions. And in many studies investigating the fMRI recordings, it is shown that the brain employs a rich repertoire of functional networks, which are dynamically active even when they are at rest. And this was confirmed for MEG and EEG, where resting spatial structures resulted functionally overlapping to the ones of fMRI. Additionally, in the last 5 years, the static analysis of average time brain networks has been somehow replaced by the analysis of transient brain networks, showing how these cortical phase coupling networks have characteristic signatures in very specific frequency bands. However, there is still no unifying theory for the fast formation of the spectrally resolved networks. And the study of oscillations has always been interlinked with the study of self-organization. Understanding the physiological mechanisms of self-emerging oscillation not only will provide insight into their functions, but also may assist in the diagnosis and treatments of brain disorders. And drawing insights from physics, empirical evidence points to this adaptive complex network dynamics in brain activity, but we don't really know the generative mechanisms that support this dynamical regime. And it's thought that this regime arises from an interplay between local activity and long-range coupling, where collective metastable oscillatory modes are created. And on this note, brain network model have been able to explain, predict, and also integrate neuronal activity at the macroscopic scale, building on the concept that the regions do not actually operate in isolation. So we'd like to present a brain network model based on large-scale connectivity matrices at the global level, which displays endogenous dynamics observed in resting state studies. And 3 major ingredients shape the brain dynamics on the macro scale: intrinsic node dynamics, connectivity, and coupling, considering time delay. And in this reductionist approach, we see each brain region as an oscillator, whose dynamics is described by a normal form of a supercritical Hopf bifurcation, or also known as Landau-Stewart equation, a phase amplitude model that studies the transition from noisy to oscillatory dynamics. And we take the intrinsic frequency omega in the gamma frequency range, so we can investigate the link between fast local dynamics and slower global fluctuations. Second, the wiring structure reflects what we call the structural connectome, and K is a global scaling factor or coupling strength that equally scales all the synaptic connections, while the structural matrix C denotes the density of fibers between cortical nodes extracted from the DTI-based tractography. And we model these node-to-node interactions using a linear diffusive coupling and considering delayed interactions. And in this framework, the approach is purely bottom-up, so not data-driven, and we have only 2 free parameters: the global coupling strength K and the mean conduction delay tau, where D is the mean length of all fibers detected between each pair of brain areas. Then we actually perturb our model with noise in a form of a complex Gaussian noise with mean 0 and standard deviation beta. And so this is the overall methodology. First, we have the average structural matrix to inform our model. Then we run the simulations and explore the network dynamical space and play with parameters to investigate the behavior of the system, also the simulated signals and the properties. On the other hand, we analyze the HCP Human Connectome Project MEG signals of 89 subjects, extract spectral and connectivity features, and compare them with the simulated power spectra and also functional connectivity for each band of interest. We then measure the spectral fitting and also the connectivity or spatial fitting. For one of the optimal points, we also investigate the ability of the model in detecting what we call the metastable oscillatory modes. And our first analysis shows that collective frequencies emerge from synchronization in presence of delays, in alignment with the analytic prediction of a really nice equation presented by Niebuhr in 1991. They actually analyzed the dynamic behavior of large two-dimensional systems of limit cycle oscillators in presence of time delay, and they find that even small delays times lead to a form of frequency depression where the system decays to the stable states which oscillate a reduced collective frequency. So here we evaluate the degree of phase synchronization of the system by using the Kuramoto order parameter. And for the range of couplings and delays explored, we report the mean and the standard deviation of the order parameter, referred here as synchrony and metastability accordingly. And in addition, we report the peak frequency of the global signal and the predictive collective frequency. So for weak coupling, the simulated signal exhibit only noisy-driven oscillations, peaking close to the node's natural frequency. No sign of synchronization, and the peak frequency stays around 40 Hz. So we don't observe strong fluctuation in the Kuramoto order parameter. For the intermediate coupling, weakly stable synchronization generates these transient oscillations at reduced frequencies, and we observe the fluctuations in the order parameter, which is indicative of metastability in the system. For strong coupling, the global synchronization becomes stable and all units are entrained in this collective oscillation at reduced frequency. And again, low fluctuation, so much low metastability. And to address the spectral predictive validity of the model, we show that this model approximates the MEG power spectral density from resting individuals in a critical range of parameters. So after taking the average power spectrum of 89 HCP subject and the power spectra for each pair of the parameters, so the K and the tau, we measured the squared Euclidean distance between MEG and simulation power. And asterisks here indicate the sets of parameters that optimally approximate the MEG power spectra of each of the 89 individuals. So here the size of the asterisk is scaled according to the number of subjects in each point. And now if we want to focus on one of these points in the optimal range and we want to investigate the simulation in temporal space, what we can actually see is exactly something like that. We find that metastable oscillatory modes are structured both in space and time. Specifically, the units synchronizing together exhibit the simultaneous emergence of an oscillation at the sample and the same collective frequency, leading to this vertical alignment of shaded areas, which is particularly visible for the alpha frequency range here. And notably, for different sets of parameters, the configuration changes strongly accordingly on where you move in the parameter space. And for each frequency band, the threshold here is defined as the 5 times standard deviation from the amplitude in the same frequency band of the simulated signals where no delays were considered. So the baseline is no delays here. And on the contrary, if we, for example, move out of the optimal region, we see that the global delta waves emerge for stronger coupling. So in a way, beyond the range where the model best approximates healthy awake brain activity, we find that higher coupling enhances global order, where the whole brain displays low coherent oscillations in the delta range. And this nicely approximates the most powerful brain rhythms detecting during unconscious states, such as low wave sleep, coma, or also anesthesia. So in a way, we could characterize the modes emerging from the system for different sets of parameters in terms of duration, size, and occupancy for each frequency band. And this demonstrates that the same network structure, in our case, the structural connectome, can exhibit different oscillatory modes organized in space and time, depending on the global parameters also of the system, in this case, global coupling strength and the conduction delay. So now that we built this initial theoretical framework, we'd like also to establish the predictive validity and the model applicability. And to put the work in perspective, I will quickly present some preliminary steps of the follow-up analysis. And here we ask how so far the functional connectivity of our raw simulations is somehow similar to the state-of-the-art MEG functional connectivity. And to do so, we needed first to source reconstruct the MEG data, then measure the functional connectivity for both MEG and the model. In this case, we measure the functional connectivity for each pair of parameters. Once we have this estimation, we can perform the model screening, which is actually consists in taking this FC and search the optimal point in the parameter space. So for example, we can see that the best approximation for MEG broadband is found in this precise point, so the red asterisk. The same can be then computed for other bands, and we can notice that the optimal region we found before holds also for this analysis. And here the maximum correlation is 0.52, and on this line, on the short term, our aim is to see how to improve the spatial fitting, try to reconstruct the simulation in the same way that the raw MEG signals were reconstructed, and also address the temporal fitting, aiming at applying the hidden Markov model on both data and simulations. And in parallel, and also Marcus' note, we'd like to run this analysis on different level of detail, which is the mesoscale level. And taking into account the excitatory-inhibitory balance can inform and add further spatial detail to our simulation. So it'd be really interesting to explore how this dynamics holds when diving deeper into brain structures. And also on the long term, would be really interested in investigating the global impact of local perturbations and definitions of brain states together with the whole brain modeling and the control network theory allows the systematic study in silico on how brain stimulation can force transition between different brain states. And in this model actually allows for a rich parameter exploration. For this reason, hierarchical modeling of cortical and subcortical oscillatory activity could pave the way for more specialized investigations of the dynamics and also targeted brain structures. And with this, I finish my short presentation. I'd like to thank my supervisor, Professor Vladimir Litvak, and my collaborators who have made this project an amazing adventure, and also thank to the Neuromatch conference organizers for giving me this opportunity. Thank you very much for your attention, and I'm ready for taking questions.
Wonderful. Thanks for the great talk. I'll be clapping loudly for everyone, as loud as I possibly can. I would like to start with a question here by Jennifer Sarah Goldman, who asks, nice results showing the effect of global coupling on the oscillation frequency. Have you compared this to data from different brain states? Have you looked at the effect of perturbations? In fact, you may be able to resolve the apparent paradox here. Why networks may be more Kuramoto type, coupled in unconscious states, but less coupled in the sense of transfer perturbations between regions as they are entrained at slow frequencies.
Okay, so yeah, I mean, we didn't look.
It's multiple
questions.
Yeah,
there's a lot inside, but we didn't look at perturbation yet. That's the aim, actually, because my lab works with deep brain stimulation. So this model, in a way, allows, because it's not only a phase model, so it's not a Kuramoto model only, but we added another degree of freedom, which is what we call the bifurcation parameter, which is A, which in a way scales the amplitude in a different parameter in different points in the parameter space, but also can modulate locally the amplitude of the signal. So for example, just shifting the A parameter for all the brain areas or the brain areas included in the parcellation, but we didn't look into this in detail yet because we still need to validate really the model in EEG and fMRI. Although for the fMRI case, it's not that the delays are not so important, but it seems that they are less important since we are considering a signal which is much more slow than the MEG one. So I'm not sure if I answered that question because it was a broad one, but I'm happy to discuss in Discord if you're there.
Great. Maybe I want to ask one question of my own. I'm curious about how to fit the models, which is, we have from functional connectivity. Functional connectivity is the correlation matrix of the brain. And in a way, in your model, if I understand it right, it's easy to see what the correlation matrix again is. So how does the logic work? What do you put in, and how can you, in the end, then, if you want, independently test how good your model is?
Yes, well, for the functional connectivity part, I will say that the aim and also the suggestions for example, Mark Warich group in Oxford and all the MEG experts is to take this MEG signals and the simulations and project them to sensor and then reproject them to source in the same way that the MEG pipeline was projected. So in a way to drive a little bit that simulations. And so then the fit can be done on different level, which can be the FC static, but the most important one would be the dynamic one, the functional connectivity dynamics, and together with the hidden Markov model for each brain state. So that was now the analysis is going in this direction, but there is also the fMRI part, the stimulation. So it's a broad thing. Yeah.
You're combining data broadly. Well, this is a wonderful part of the overall panel, if I may say so, that if you want in each of the talks, I think we saw very nicely working with data, making sense of data through computation and modeling. And I think that in that sense, this was wonderful, a very Neuromatch type session. It was a great honor for me to modulate that. And let's just maybe say one last thank you to our 3 wonderful speakers. And I'll be doing that for everyone. And thanks, everyone. And enjoy your break. And we'll see you in another 10 minutes, I think. Bye-bye.